All right, we are at section 15.3, electric fields, and we see here that we have a source charge. You can see it has a bunch of positive charges on it, and we have this test charge Q0, and you can notice that the test charge is just here to determine the electric field uh, that is present from the source charge, and you can see that the test charge is a positive charge, and it is indeed repulsive from the force is repulsive, and the electric field is in the opposite direction, or it's away from the positive charge. You here, if you were looking at here, the electric field would be pointing upward, but what they're showing you here is that this charge at here would cause these charges to move away from it. So the electric field is equal to the force divided by this Q0, and this is newtons per coulomb. The units are newtons per coulomb. Let's see if I missed anything. Okay, that looks good enough. Okay, so E is defined, you see the triple equal there, the force divided by this Q naught, this test charge, and again, it's newtons per coulomb. Okay, electric fields, if it's a negatively charged particle, then the electric field is toward it. If it's a positively charged particle, then the electric field is away from it. And let's get back, let's see where the force is equal to QE. Let's stop this chair and let's go back to that little simulation. There it is again, way down there. And let's put a test charge, and these are the electric. They even call them the electric field. You see, we turn it off. They're not there. We can turn on the electric field. And now notice that the closer you are to the charge, the arrows are whiter, if you want, and they diminish. So the electric field is diminishing as you move away from it. And let's take our test charge again, and if we move it again, the test charge is positive. You can see how the force, as it goes off the screen, it's so strong. The force, and this is just a 1 nanocoulomb charge, the force is inversely proportional to the square of the distance. Let's move a negatively charged particle over here, and if we put the same, let's move it a little bit more to where it's between the arrows. If we move it, the test charge over here, you can see that it's attracted to the negative particle, and if we move very close, it goes off screen, and as we move away, it diminishes, not quite to zero, but very, very small. So that shows you the same action that we've just discussed. Let's go back to the lecture and move up here. Okay, if Q is positive, the electric field at point P points radially outwards from Q. If Q is negative, the electric field at P points radially inwards towards Q. So we were able to see that in the simulation, the FET simulation. And let's go. So it's going to be along a line joining the two particles. And the force is equal to Q naught, KE times Q naught divided by R squared. And the field, the electric field, notice that electric field is there irrespective of whether Q naught is there or not. KEQ divided by R squared. Okay, and the electric field between two like charges is equal to 0. Let's set this up. Let's change. Let's do a new share and go down to, let's just simulate this. Let's clear it. Let's do a grid so that we can be more precise. Let's put one right at the center there. And let's put one, there's 4. So right here, let's take our sensor. Oh, notice that if I move just a little bit to this side, the force is on over there, and it really disappears there, and then it starts to grow in this other direction. So the electric field right here between them is 0, just like as it said in our notes. Oops, let's share the other screen. So you can see you have Q, and we went right in between, and the electric field there was 0. So let's come up with some problem-solving strategies. You draw. The best thing is to draw your situation, including the intensity of the charge and the distance, any distances related to the charge. Identify the charge, whether it's positive or negative. Convert all units. Apply Coulomb's law. Sum all the x components, sum all the y components, and use the Pythagorean theorem and trigonometry to come up with it ends up being a superposition. So it's just a vector addition of all the forces that are there. And I think that's it for this section. Yeah, the next one is electric field lines. So we'll stop here, and the next one will be electric field lines.